Hello everyone, welcome back. In this lecture we're going to be discussing about linear programming problem and simplex algorithm. Before we discuss the algorithm for solving linear programming problems, let's have a look at the kind of problems we are talking about. Imagine a company manufactures some bottles, okay, and two kinds of bottles. Company manufacture glass bottles and steel bottles. Company can make total of 30 bottles per day, and it has 60 labor hours per day available. Okay, it takes 1 hour to manufacture a glass bottle and 3 hours to manufacture a steel bottle. Company makes $3 profit on a glass bottle and $5 profit on a steel bottle. All right. So in this kind of problem, essentially company is looking for maximizing their profit. And how they're gonna maximize it, that if they manufacture bottles in optimal ratio of glass bottle versus steel bottles, which maximizes their profit equation. So if we have such kind of problem and we want to solve it, so what is the step first? Step first would be to identify the variables. Okay, so let's identify the variables in the problem. So as we can see here that we have glass bottles and steel bottles. So one variable would be glass bottle, which we say x variable. Another variable we can say y, representative of steel bottles. All right. After identifying variables, what we're gonna do next step is to form equations. Okay, very simple. That company manufactures 30 bottles per day. Okay, so total bottles, glass bottle x plus y, steel bottles, should be less than 30, cannot be more than that, okay, or equal to 30. Second equation, that 1 hour it takes to manufacture a glass bottle. So 1 multiplied by x, which is a representative of glass bottle, and plus, and it takes 3 hours to manufacture a steel bottle. So 3 multiplied by y is less than 60, because we have total 60 labor hours available with us. All right. So that is equation number 2. And third equation would be simply our objective function, or what company wanna do. They wanna maximize their profit. So we're gonna have a profit equation, and how that $3 profit on glass bottle and $5 profit on a steel bottle. So total profit would be 3 times x plus 5 times by y. All right. Now, how do we solve it? Okay. So third step, it's a very simple problem. If we try to plot it, okay, plot a graph between x and y variables. So as you can see here, this equation represents a line. Okay, this is the equation of a line. So let's see if we plot a graph. All right. So how the graph would look like? Say on x, between x and y variables. So for this equation, x plus 3y less than 60, the graph would look like as it is shown here in this graph. Okay, so it intersects on x-axis at 60, and it intersects on y-axis at 20, this line. Similarly, if we try to plot a line represented by equation number 2, which is x plus y is less than 30, which intersects x is 30 less than or equal to 30 uh, and y is less than or equal to 30. So, what it means that these inequality constraints or less than or equal to constraints, this constraint means that the value of the x would be less than or equal to 30. Same way, value of the y would be less than or equal to 30. Okay. So, in the same way, we can say that the equation number x plus 3y less than or equal to say is 60 says that the value of the x is 60 or less. Okay. And in this, we are assuming that the both variables x and y, they will have minimum value 0, or our solution would have the positive values of x and y. Okay. So, x is between 0 to 60 if we take equation number x plus 3y is less than or equal to 60, and x is between 0 to 30 if we take second equation. Same way for the y. So, interestingly, you see here we are interested in the area, okay, which is common between the axis and the intersection of these two lines. So, essentially this area we are interested in. So, we are going to find our optimal solution for the profit within this area. Okay. We can choose any number of value, any number for the value of x and y within this area. All right, and these two lines intersect at this point. So, that is what this whole system of equation represents. So, now say there may be many possibilities of the value of x and y within this area. So, how do we find the value of x and y which maximizes our profit? So, that is what we mean by these equations. Okay. So, let us try to put the values of x and y in the profit equation. So, as you can see here that in this area, see the minimum values of x and y are 0, 0. So, we are already assuming that we're going to manufacture, or company going to manufacture bottles more than 0. Okay. So, this point we can omit. Then another point of intersection would be this point where y equal to 20 and x is 0. Another point of interest would be when x and y are 15, 15, where both line intersect, and third point would be where x is 30 and y is 0. Okay. So, this whole area is bounded within this region. Okay. Is bounded by these points. So, if we calculate the profit at these points and then try to find out what is the maximum value of profit, that will give us the answer, as simple as that. So, let's say the objective function 3x plus 5y, and at first point 30, when x is 30, y is 0, the value is 90, when x is 0, y is 20, value is 100, and when both lines intersect at point 15, 15 is 120. So, as you can see here that the minimum value is when the variable x takes the value 30, means we are going to only manufacture 30 glass bottles, we will have minimum profit. Okay. And then if we manufacture 15 glass bottles and 15 steel bottles, let's talk about a general structure of such problems. In simple sense, we want to maximize we want to maximize this equation. Our objective function is in the form that the variables multiplied by some coefficients added together, subject to certain constraints. Out of those constraints, the first constraint is that all variables will have positive value, and each variable multiplied by some coefficient added together, satisfying this satisfying the constraints, different constraints. Okay. So now A is some constant or coefficient, and B is again some constant or value. Okay. And see here this less than or equal to sign. This makes our life a bit uneasy. So if we change this form, okay, into another form where we got rid of, or we get rid of this less than or equal to sign, and we just make it equal to sign, that will make our life easy, and we would be able to solve easily. Okay. So if, for example, if we take this whole left hand side, okay, and take it to the right hand side, and left hand side we introduce new variable. Okay. So how it will look like? It will look like this. Now this form we can solve easily because here we have equal to sign. Okay. With this equal to sign is saying that, okay, we want to find the solution for the variable s using these equations represented by s equal to b minus whatever was on the left hand side in our constraint came to right hand side. And this form we call slack representation, and variable s is called slack variable. And we put a constraint on slack s variables in the same way like we put a constraint on x variable, original problem variables, that its value should be greater than or equal to 0. So typical linear programming problem, any kind of linear programming problem, we would like to have slack representation, okay, for those problems before those can be solved by our computer program. All right, let's take an example. For example, we want to maximize this equation 3x1 plus x2 plus 2x3, and we want to find out the values of x1, x2, x3 which maximizes the objective function represented by this equation. So, or you can say my objective function f represents this, or f equal to, and we want to find f max. Okay. So we want to find the values of x1, let's call it x cap, x2 cap, x3 cap, which maximizes the value of objective function. And this is subject to certain constraints, and the constraints are represented by these equations. All right. So step first, convert these constraints into a slack form. Okay, slack representation, and introduce new slack variables. So we introduced x4, x5, and x6 new variables. Now notice here that each of these variables, x1, x2, x3, x4, x5, x6, these cannot have negative values. So minimum value what these can have is 0. Okay. And our original variables are x1, x2, x3. So if we try to find the solution for x4, x5, x6, and one solution when x1, x2, x3 takes the minimum value is 0. So that solution we will call a basic solution, and the basic solution, if we put x1, x2, x3 equal to 0, then we get x4 is equal to 30, x5 is equal to 24, x6 is equal to 36, and z is equal to 0, our objective function. Now see here, if we get this solution of these basic variables or basic solutions of these variables, which includes our slack variables x4, x5, x6, then we put the solution back into original equation and find out the what is the value of x1, x2, and x3, and substitute it back to our objective function. We can find new value of our objective function, and we can do it iteratively, maximizing z. Let's focus on the objective function now. So what it says that, okay, x1, x2, x3, it can take infinite number of possible values, but minimum value of x1, x2, x3 is 0, and using that 0 value we found the value of x4, x5, and x6. Simple. Now our focus would be to take these one of these variables x4, x5, x6 and substitute back these variables into our objective function equation. Okay, or in simple sense, we can say that select a known basic variable. Known basic variable would be x1, x2, and x3, okay, in the objective function whose coefficient is positive. So let's say we select x1, okay, and the value of the x1 from the equation, this last equation, if we try to find, so let's see how we can do that. So if we take, we were focusing on x1, and we can find out the x1 from third equation in terms of x6. Now here, see, x6 has the negative coefficient, means that if we increase the value of x6, it will decrease the value of x1. Okay, and if we substitute x1 to z, then we would have negative x6. So we can't increase the x6, otherwise it will make our objective function value lower. So this sort of thing is called pivoting. So we are trying to find pivot variable, or which enters into our solution, or basically we find the new variables which enters on left hand side, which is our basic variables, and right hand side are our non-basic variables. All right, now since x1, okay, x1 was non-basic variable and it is entering into a set of basic variables. So we call it xe. Okay, e is simply entering. You may think of in that way. So variable x1 is entering into our basic solution, and variable x6 is leaving from our basic solution, basic variable set. Okay, and we substitute the value of x1 in our problem equations. So we substitute x1 in all rest of the equations and find a new set of equations, okay, with new set of basic variables and non-basic variables. Okay, so these variables are basic. So in the first iteration we did that. When in the next iteration we would get rid of this another variable x5 slack variable, which is our basic variable now, and introduce new basic variable and then x4. Okay, until we find that we can't optimize or maximize the value of our objective function. Now let's see how the equation would look like. So we substitute these values. Okay, so our objective function would look like this, and then x4 and then x5. All right. Now as you can see here that in original equation of the objective function, we had all x1, x2, x3 with the positive coefficient. Means if we keep on increasing the value of x2 or x3, the value of the objective function would keep on increasing. But now having a negative coefficient here means that we cannot increase the value of x6. If we increase the value of x6, it will lower down the value of our objective function. Okay, so you got the idea. So we want to have in this objective function all the variables with the negative coefficient, and once we reach at that stage, whatever solution or whatever values we have for our variables x1, x2, x3, x4, x5, x6, that will give us the optimal solution. So we keep on iterating till we find all variables in our objective function have negative coefficient. All right. So now let's focus on another variable, say x3. Okay, x3 has positive coefficient, and we can get the value of x3 from this equation in form of x5, because see we already got rid of x6 is in our non-basic variable set, and x4 and x5 are remaining variables which are slack variables in our basic set. So let's focus on this. So we find the value of x3 in terms of x5 and x6 from this equation. Okay, and we then, after finding the value of x3, we substitute the value in our objective function equation, and our objective function would look like this. All right, now see here we got rid of of the term which had a positive coefficient x3 from the objective function. Now we have x5 and x6 which have negative coefficient, means that we can't increase the value of x5 and x6. If we increase, it means it will decrease our objective function value. Only variable left here is x2. Okay, so somehow we need to get rid of this variable which has positive coefficient. And using the same procedure, that one of these equations will give you the value of x2, and then substitute back to z. So our goal in each iteration is to reformulate the linear program so that basic solution has a greater objective value. All right. So now let's focus on x2, how to get rid of this x2. Okay. So if we take the value of the x2 from this equation and substitute it to our objective function, we get a new set of equations. Okay, we reformulated our linear program. Now, bingo, here we have every variable with the negative coefficient, means we cannot increase the value of these variables x3, x5, x6. So that means that whatever solution we have right now, the basic solution would give us the optimal value or the maximum value of our objective function, which would be 28. So in this solution, basic solution, we have x1 8, x2 is 4, x3 is 0, x4 is 18, and g is 28. So as simple as that, that's our optimal solution for this problem, where x1 8, x2 is 4, and x3 is 0. So that will give us the optimal solution. Now let's talk about the algorithm. So pivoting step is important, and once we have that pivot step solved, we can use that subroutine for pivoting in our simplex algorithm. So let's talk about pivoting. Very simple. What we did so far, this algorithm is doing the same thing, that first compute the coefficients of the equation for the new basic variables. Okay, and the second step would be compute the coefficients of the remaining constraints. Okay, after doing that, third step is just simply compute the objective function, and you get the new program. Okay, new set of basic and non-basic variables. So n is nothing but a set of non-basic variables, b is a set of basic variables, a is your coefficient matrix in the original program, b is your right hand side vector, c coefficients vector for the objective function, v the value of the objective function, l is the subscript denoting the leaving variable from the non-basic from the basic solution set, and E is the entering variable into the basic variable set. Okay, and how we can write the simplex algorithm? Very simple. That we take the original problem, means that the matrix of coefficients, okay, A, which are our constraints represented by constraint equations, B and C, which we discussed earlier, that in the matrix form, how we can represent the system of these equations. Okay, and then we basically get in the basic set, non-basic set, value of the objective function to start with, and rest of the procedure is just simply saying that we keep on doing the iteration till we have no more variable left to enter in our basic set, and we keep on finding the new pivot. Okay, and in the end, when we finish, we just return the basic solution set. Thank you guys for listening. Thank you for your comments, and thank you for subscribing Lee Professor on YouTube. Those who have not subscribed, please do so. We appreciate your support and feedback. Have a wonderful day.